And a good morning to everyone. And we were listening to the Grateful Dead, Uncle John's band, and wouldn't mind just listening to the rest of that album for a while. We are doing graphene, and the question, why are we doing graphene, has been asked. Well, there are several different levels on that answer as to why we would spend time looking at a linear equation in two variables, and why would we spend time just developing this expertise, this ability to do a graph. Algebra sits as a course content in beginning algebra, providing material, information that is necessary for different involvements you may have after this course. Now, if you look at algebra as a language of analysis, we get interested in looking at areas which I've referenced briefly, like the calculus. And there's a very interesting kind of problem that comes out of calculus called minimum-maximum problems. And in a practical level, if you were looking at, and I can't help but noticing coffee got, I'd never do that.
That's not coffee.
If you were looking at packaging in a cannery, and you're going to produce a can of tomato paste or a tuna can, I hope as I've said those two examples, you have a mental image of a tuna can and a tomato paste can. They are nearly antithetical to each other, opposites in a way. The tuna can, fairly flat. Doesn't have a very big height, but it has a large radius. The tomato paste can, that traditionally was known by the Contadina label, is very different in the sense that it is a can which has a painted label rather than a paper label. So the question, you have certainly brand recognition, and if a person goes up and looks for a can of tuna and it looks like a tomato paste can, they may not be inclined to buy it. So there are issues about how you create a product for recognition. But if you take that aside and you ask, what shape of container would I use given that the amount of paint I can afford to put on the label is a constraint? What should the shape of that can be to minimize the paint while I'm maximizing the volume? Now that's not an easy question to answer. And so we get to questions like, if you're going to have a rectangular shape given a certain perimeter, what's the maximum area you can get? What is the best shape? Well, those are problems that are analyzed using equations in which you have a variable and you are going to look at the graph involved. So try to bring it down to a little less sophisticated level when we talk about gas mileage on a car at different speeds. I think you realize that when you're in McHenry Avenue, the gas mileage isn't good. And when you're doing an illegal speed on I-5, your gas mileage also goes down. In one case because you're going too slow, in the other case because you're going too fast. We have talked about a linear equation giving a line. There is another equation that's a very interesting kind of counterpoint. Now here's the simplest equation for a line I can write. That happens to be a line through the origin. Here's another equation that's two variable but is no longer linear. And it has this equation, y equals x squared. Now this is a very recognizable equation for anybody who has looked at the Golden Gate Bridge. When you look at the cables on the Golden Gate Bridge, you see an arc, and that arc is known as a parabola. That particular equation gives a parabola. So if I look at the plot of the pairs of numbers that satisfy this second equation, I get this shape called a parabola. Okay, so this is the end of the semester topic, but just as information, it is the shape that is very interesting and known to you. If you toss something like a baseball and throw it, it follows a parabolic arc. So if I were to toss an eraser up in the air towards the back of the room, the arc that it would follow would be a parabolic arc. The difference is it would look like this. That is, it's opening downward. So this is called opening upward, opening downward. Concave up, concave down. Now, if I think of this not going through the origin and just look at a more general case, say something like this, then I'm interested in where the maximum height is obtained. And that occurs over here. Now, to assess a maximum height could be a very important issue in artillery, because shells being fired at a particular angle follow this arc as we're going through. And depending on what limitations you have with aircraft flying over, that becomes a big issue. And that is a problem analyzed using an equation, and this more general equation will be of the form ax squared plus bx plus c, and that is a general equation for a parabola, and it's the language that we use in graphs to help us solve very practical problems. So maximum height of this shell that is being shot at a particular velocity and knowing where it's going to land over here, producing a can which is going to have a certain volume given a constraint on how much paint you can use for the surface area. We look at problems in maximizing and minimizing the volume, the distance, the height. These are all problems that require graphs as part of the analysis. So in a sense, this process that we have started lends itself to further study in mathematics. And of course, that may be gilding the lily here a little bit, in the sense saying my assumption is that you'd be going on into another course. I would assume that you would certainly be preparing for Math 90, because that is the sort of a demanded prerequisite for any course that you're going to take that transfers. So let's look at it from another area, not in terms of future academic involvement in mathematics for the sake of doing something in mathematics, but perhaps looking at it from a business perspective. Where would you use this kind of course content if you were going to think in terms of a world involving you in a business community? And there are two areas there that would be potentially involved. One is in spreadsheets, using Excel, using certainly still available through IBM as the Lotus Suite with the Lotus 1, 2, 3, but you've got Excel, and you do surprisingly track such things as costs or profits over a period of time. And you try to set up some relationship. Okay? And one of the most important relationships is a linear relationship. So you would take, for example, the amount of money you spent in advertising, and you look for what? An increased revenue. The hope is the advertising paid off. Or you may look at advertising and you look at sales. And so the argument is, as advertising goes up, you hope sales go up. That is what we call direct variation. And we've already looked at the equation involved there. That's y equals k times x. And there is the hope, and then there's the reality. So if I look over a period of months at the amount of money spent in advertising, and I have somebody who's a very good salesman from either a newspaper or a radio station or a television station saying, invest money in this, we will guarantee you more revenue, more sales. And of course, that's what's been done for next weekend. This weekend coming up, the Super Bowl. And so you have companies saying, if we advertise in the Super Bowl, it's going to cost us like crazy, but what's the hope? Huge audience watching, therefore the revenues you hope for the product you're advertising will increase. Now, we have a name for this analysis in statistics. It's called bivariate data analysis. So let me, in short term, look at the space behind me on the board now. As you're looking at it, Ernie, it'll be to the right side. And what we're going to do is just consider for a moment some data that you might get. And boy, that is the sickest looking organ attempt at an axis I've done in a while. So let me try doing a little bit better here. And so let's say this is advertising and this is sales, or maybe even it's units sold. And so you start out with a low amount of money invested in advertising and you find your sales aren't very good. A little bit later, you invest a little bit more money and you get more sales. Well, we just had those 2 points. It might suggest that there's what? Some kind of linear relationship there, suggesting then put more money in and get more sales. Just keep investing. Well, as you track this, maybe the next point's here. Not quite on that same line. And then maybe later there's another point up here, another point down here, maybe a point here. And what you find overall is a kind of linear pattern. This is called a scatter plot, where you plot a lot of points. And then what you try to do is fit a line through these points so that the line, well, crosses, in a sense, as many points as possible, but another constraint, that the distances from the points to the line, vertical distances, are kept as small as possible. Now, this next week in our stat course, we're going to go through this content, and we are going to try to create a line in the form. And what form is this? You recognize it at this point. We had a name for it. Okay, I'll put it in the other form. Let's see. We had, starting with this as an equation, we solved for y, and what did we get? This is in your notes. We had that y, and I'll write it down here now, y is going to be minus a over b times x plus c over b. What did I call that form? Slope-intercept. Precisely. That was the SI. Not Sports Illustrated, but slope-intercept. This is the form of a line, the equation of a line, linear equation, 2 variables. Now we try to find the line that fits this data. We kind of call it the line of least squares. And in the business community, we try to take such an analysis called bivariate data analysis. If we can find this particular equation so that it fits the data, keeping these distances as small as possible, we have a line, we have an equation now that allows me to predict for the future. So if somebody says, and oftentimes this is in management, the person who's related to the accounting operation, the proverbial bean counter says, well, our budget for advertising is going to be $1 million this year. Then what does management want to know? If I invest that money, how many units can I anticipate in production, and what constraints does that involve in materials, personnel? We want to predict. And we do it through the same line we're talking about. And so to that extent, even if you don't take a stat course, and you sit there in a business setting and you track these numbers. And what's nice is you can put them into Excel, and Excel will create this equation for you and will give you the line. And so your understanding of what goes into that line and how to then say, if I have it in this form, I have some number times x plus some constant, then it says I know how I can substitute a value for x and get y and predict my sales in the future. And that is a problem whether you're running a business in your own or participating in somebody else's business, is a very serious problem to assess. What's interesting, if I take the same information I talked about with the mileage for a car, and I said you get a parabola. If you plot the points, you travel 10 miles an hour, here's your miles per gallon. You travel 20 miles an hour, here's your miles per gallon. So you get a table. We would have entries, and I'm going to again go over here further to the side. I would have entries something like this. Here's my miles per hour, and here is going to be my, what do we call it in terms of, you travel 55 miles per hour and you look at your average, how do I want to say that? If I go to the gas station and I pay $30 for a tank of gas and I've had 10 gallons, okay, then we talk about miles per gallon rather than miles per hour, right? Mm-hmm. So I don't know if I want to call that the efficiency or however, but you understand what I mean by now a miles per gallon measurement. So you hope you can get 30 miles to a gallon, 40 miles to a gallon, and of course the whole industry is trying to get sort of an elusive 100 miles to a gallon or something. I guess the ideal would be 1,000 miles per gallon. Buy a gallon of gas and go forever. Well, if you do 10 miles per hour, what kind of miles per gallon typically in a, take something like a Camry, a Civic, maybe an Accord, but medium size, an Accord or something from Honda, Camry from Toyota. What kind of miles per gallon do you think you're going to get doing 10 miles per hour down McHenry hour after hour? What if somebody says you're going to get 30 miles per gallon? What's the range they usually talk about? Well, between 20 and maybe 40. So the idea is you might hope somewhere around here that at this worst case scenario, this is horrible, 15. But if you can drive around the city maybe at 20 miles per hour, this is going to go up to what? 20 miles per gallon. And if you can go 30 miles per hour, you don't want to do this in the freeway, but maybe this creeps up to what? 25. And then if you can get out in the freeway and do 50, you maximize out at what? That 30. And then if you start going in the freeway a little bit faster than that, maybe go 65, what's going to start happening? It starts going down, and if you're at 80 miles per hour, maybe it's coming down to 20 again, and there's some point at which it starts dropping and it levels off. But if you plot these points, you're going to get that parabola. So if we come back over here now to what I have on the second parabola to the right, okay, so we're going to click over there. If I come to this one, and wait for Ernie to catch up with me, okay, then this might be standing still. Okay, so this is your miles per gallon if you are in the driveway warming up. Now, this is going to be maybe what happens at 50 miles per hour, and you get the maximum out here at 30 miles per gallon. And then I guess this is where the engine blows up. So you're doing maybe 150 miles per hour in your Civic, and the engine just blew. And so your miles per gallon is down to 0 again. That is a different model than the revenue model, or the number of sales I get out of advertising, the number of units sold. So each of these graphs relates in a different way. And the obvious issue is if you could plot points, you could get a pretty good idea where your maximum occurs without doing any sophisticated analysis. In the same way, if I think now, coming back to this graph now, I don't know if you want to change cameras on me, or, okay, I need this one right here. Then even without knowing what this is going to give you as a graph, you might what? Still be able to sketch a line through it and find the equation of that line. And indeed, what I have students doing next week in the stat class, plot the points, draw the line through it, and try to estimate the equation of that line. So the equation of the line down here, the place where the line crosses the axis, gives you your intercept. The only other thing you have to do is to try to see what the slope is. So you go from this point to this point, and you ask how much has y changed, how much did x change, and that's going to be called the slope. It's called the rise over run, and that becomes this coefficient. So in a sense, what we're creating is a language. We are creating the background to discuss problems that are very useful. Of all the things you'd ever take in algebra, there could be an argument that this one introductory level beginning algebra course provides you enough information, because I'll cover both these problems, the line and the parabola, during this semester in fairly decent detail, give you enough that you can use that information in a very positive way with no other courses in mathematics. What's interesting, if you think of a calculus course, coming back to this problem now, we find the tools to guarantee that what's obvious to you visually is indeed the maximum on that height. That this point, if it is at 50 miles per hour, will come out as an analytic process doing some of the same kinds of manipulations we talk about in this course. It's just you have a lot of space in between. So, in a sense, we're learning language. If you ask, why should I take a course in English? Communication, the ability to speak clearly, to communicate ideas and do them well as the communication, becomes a very strong defense for having courses in language. And if you're going to write a novel, you're going to write poetry, you're going to try to write about elegant ideas, you need that vocabulary, you need that language, you need to understand sentence structure, punctuation, and all the things that go with what we talk about as an English course. If you're going to communicate on a quantitative level, you need the language of algebra in the same way. It provides that ability to talk about ideas that are very difficult to quantify without the language. So that's the defense, in my view, for why algebra is worth knowing. How far you go on that? A little bit like how far you go in language study. It depends on what your goal is going to be. If you're going to write a novel, you're going to write poetry, and you're expecting to do so at a very high level, then you take more courses. If you want to get very sophisticated in the analysis that goes on, and you want to do more than talk about mileage in a car, and you want to be talking about aviation and looking at a plane taking off, coming up, landing, going from the Modesto Airport to the Stockton Airport, and doing it in the most efficient way, suddenly you need a greater sophistication than you do in this little problem about cars. What's the minimum level that we argue that's reasonable? The intermediate algebra, because there are two different things that happen in that course that don't happen in this course. We've taken a second degree equation and a first degree, what we call a linear and a quadratic, second degree, first degree. But if you look at growth, how is Modesto growing? How do populations grow in general? We get to what is called exponential growth. And I'm going to take a little bit, we're going to scoot over now, Ernie, to the left, my parabola equation. An interesting little question might occur to you on an evening when it's raining and you have a nice glass of wine and you're just, you know, sort of, what's the phrase we talk about? Relaxed. You're just sitting there letting your mind wander. And you might ask, just might, maybe with 2 glasses of wine, what would happen if I changed the position of the x and the 2? Simple reflection. This is 2 to the x, that's x to the 2th, the second. Okay? This becomes a most interesting equation because now, related to this one, is this curve. Exponential growth. Now there's a classic problem that goes back, some of you may have heard, at some point, Sessa's reward. And you've heard it as a kind of interesting little brain teaser. If I agree to pay you 1 penny for the first day you work for me, and double that the second day and pay you 2 cents the next day, the third day I'll pay you 4 cents. By golly, in the 4th day you even get what? 8 cents. Would you work for me for 1 month? And the usual reaction is, get real. You aren't paying me enough. But by the 30th day, you are so rich, it's disgustingly rich. It's 2 to the 29th power divided by 100. And that number is huge. Okay, we're talking more than 1 million in your 30th day. Makes up for the penny you got the first day. Now this is exponential growth. That's how populations grow in the world. And our whole topic in the STAT course is the world population in crisis. Because we've been growing exponentially. And the question that faces us now, because we're at 6 billion, how soon before we're at crisis level with too many people? We already know we have too many people in California for the water we have, but we keep growing. Where does it become such a crucial issue that your resources don't meet up with your population? And we see it on an annual basis here when we have what? Droughts. We don't have enough water and suddenly it impacts on us. What happens when the air gets so dirty you can't breathe it and you don't go outside? It impacts on us. What happens when there's not enough water and we have rolling blackouts? And we're paying the price this year because that big surplus we had when we paid for the blackouts of just a short time back has us as a state economy in a rather difficult position because what is our deficit right now? How much short are we? The figure, 36 billion? That's one figure, somewhere around there, and that's the argument that's affecting this state as we ask, where is the money going to come from? As a district, we're sitting there short 7 million. 2 years ago, we had surpluses. What's happening? Growth, demand, and we don't keep up with it. This becomes intermediate algebra. And oh, by the way, there's a related curve that I'll draw that looks symmetric to a 45-degree line, and that's called a logarithm, a logarithmic function, and those two functions become the essence of the intermediate algebra course, and these two become a way of explaining the world around us. Graphs, are they important? You're talking about understanding your world and what's taking place. The answer is a profound yes. And that's why we take the time to look at graphs. So I hope that 25-minute presentation answers a little bit of the question, why are we doing it? Now, one of the things, and Ernie, at this point, camera 2 is going to have to kick over on the side. One of the questions that got raised from yesterday's presentation, some of the things in that second set of problems seem to be a little bit beyond what we've done. Case in point, I suggested you plot 2 points. The answer key sometimes gives 3 points. Why 3 rather than 2? And why the 3 they took rather than the ones you took? Well, you have as many choices as you want, because if you have a line, how many choices do you have? An infinite number. I suggested take a couple easy ones. Take the intercepts when x is 0 and when y is 0. That works fine until my line goes through what? The origin, and now when you let x equal 0, you get y equals 0, and you wanted 2 points, and you got 1. Well, that's a wrinkle you didn't count on. What do I do now? Punt. Take another x. Any choice you want. There should be some reasonable choice. If you want to graph things on the paper you have, you wouldn't let x be 1,000. And you probably don't want to let x equal minus 3/5. So you take a nice counting number. X is 2. Find y. Now what you found, oftentimes, bless you, is that minus 2 then is used for the other value, just for symmetry. Take x at 2, take x at minus 2. Your choice can be different than that. There's no obligation. Why do you want 3 points? Well, if all 3 points fall on the same line, you're pretty sure you didn't screw up. But if 2 of your points are on the line and the other one isn't, it suggests you maybe better check what's going on here. It's called a checkpoint. If you're confident and smug, go for 2. Cut your work level by 33%. If you're a little less secure than that, and you've been trapped a couple times, then go for 3 points. If you feel insecure enough to go for 4 or 5, you need to deal with your insecurity and go back to 3 at most. Okay? Now, I'm going to go, as I say, to the sideboard because I want to address a couple issues here. One I've tried to address this morning, looking at y equals x, because it is, in essence, this form of the linear equation in 2 variables. So let's go to the document cam. ax plus by equals 0. That's going to give you no intercept, okay, because the c term's missing. So in this form, we have ax plus by equals 0. I'll write it up here on the sideboard now. And if you solve for y, what do you get as we come to the sideboard? We get y equals, okay, the ax is being subtracted from both sides, so I have minus ax. And then I divide it by b to get y by itself, so I get minus a over b times x. I talked to you about the simplest equation I can write for a linear equation in 2 variables, y equals x. The table is a very easy one to get. So I go ahead and I run this table in the following way. Here's my x, my y, and if you let x equal 1, y is equal 2. You let x equal, I'm sorry, I doubled it. If x is equal to 1, y is equal to 1. If x is equal to 2, y is equal to 2. We just go that way, right? I can get points very quickly. Now, what happens if I let x equal 0? Y equals 0, so I only have one intercept. It becomes the xy intercept simultaneously. But when I graph this particular line, again, the key here is you have straight edges. You take this quickly, you scale them very quickly. Keep the scale uniform. So 1, 2, 3. So I have my scale drawn. This should only take you a matter of seconds, certainly a half minute, minute at the most. Now when x is 1, y is 1. When x is 2, y is 2. When x is 3, y is 3. Do as many as you want. When x was 0, y was 0. All those points are on the line. X is 1/2, y is 1/2. X is 1/3, y is 1/3. Join the points, and I didn't plot them very well. That one's supposed to be there. My scale is not uniform like I thought it was. But the key here, how many points do you need? 2. Doesn't hurt to plot 3, but any more than 3, I think, is not necessary. Now, you had a couple cases where a little bit of uncertainty crept in, I suspect. What happens if I give you the equation y equals 3? What's missing?
X.
The x. Well, you could argue technically that you have 0x plus 3, correct? Make sense? No matter what x is, 0 times x is 0. It's just a missing term. But if I look at my same table now with this, and it was a little bit disconcerting if you don't have x, and you're saying, well, what do I do? I take x at 1. What's y? 3. X is at 4. What's y?
3.
X is minus 2. What's y?
3.
I don't care what x is. Y is 3. Y is always 3. What kind of line do I graph in this case? a horizontal line. So I have x, I have y, here's my scale, 1, 2, 3, and my line goes through 3, and it looks like this, horizontal line. There is no rise in this line. It's always the same height. So we say the slope is 0. Now what about x equals 3 as a contrast? At x equals 3, think of the way my equation looks again. X and y. What term's missing?
Y.
So we have 0 times y plus x equals 3. Do you see how I can rewrite that equation? X equals 3 with a y in it. So I take x is always 3. So y can be what?
0.
It could be 0. Y could be what?
3, 1,
3 if you want. X is 3. Y could be?
-3.
Negative 3, okay. X is 3, y can be 1,000,000. Because I'm going to take 0 times y. So what kind of graph do I get in this case? Again, now you should be able to do that operation with the straight edge in about 10 seconds. Okay. 1, 2, 3. Vertical line with arrows on it. And now x by itself is just a vertical line. Y by itself, horizontal line. You need to remember that for the entire semester and beyond. Y equals a constant, horizontal line. X equals a constant, vertical line. So we'll leave those two examples up there. And I'm going to go back up to the front while Ernie just holds that there for a moment on the camera. And that related to questions that were involved in 21 through 36, but here is the presentation, page 192. So the graph of the linear equation y equals k is a horizontal line going through the point 0k. And then at the bottom of that page, as we come off there for a moment, and I slide down, vertical line. And here we have the graph of x equals k going through the point k0, and it's a vertical line. That relates then to the problems you had in 21 through 36, because some of these were horizontal lines and some were vertical lines. 33 was what? Look at the screen. 33, y plus 1 equals 0, so y equals what?
1.
Negative 1. So what kind of line?
Horizontal.
Horizontal line going through 0 minus 1. Let's come off there for a moment. Over on the right side, 36. X equals 4. What kind of line?
Vertical.
Vertical line going through 4, 0. Okay. Sliding over a bit. Next one. X equals minus 2. Vertical line. Coming off that. 34. Horizontal line going through 3. It's the one we just did. That's the same as y equals 3. Ernie, can you pick up the sideboard with the camera just the way it was? Just click to the sideboard. We'll get the right board yet. Okay, there we go. And it's the graph on the left side as you look at the monitors. That was y equals 3. If you want to tweak that just a little bit to the left. A little bit more. Okay, there. We have y equals 3, which was 0x plus 3. Okay, as we come back to the front, that is what you were doing in the homework problems. Now the others were, some cases, a heck of a lot easier. For example, looking at number 30, y plus 3x equals 0. Make a table for that, and it was pretty nice, right? If x is, for example, let's come back to the document just for a moment. If x is 0, y was 0. So you got an ordered pair there. And if x was 1, y could be what? If x is 1,
-3.
y would be -3, and you'd have another point. So that would give you 2 points, and you have your line. Now, one that wasn't so darn easy is this one, 28. 6x minus 5y equals 18. Well, if you let y equal 0, That was nice because x is 3. But finding x equals 0 and y is negative 18 over 5, not so easy to graph. Did you get another pair that was nice to graph? I'm arguing that fractions aren't so nice to graph.
29 was good.
What was your choice?
29.
I'm at 28. I want to know what ordered pair works nicely there.
Oh, none.
9 what? 9 for x and what for y? 9 and 6. So that gives me 50. 9 times 6 is 54. And you used y at what? 6 minus 30? Nope, not going to work. X for 9 and y for 6. That's what I'm looking at. 9 times 6 is 54. Minus 30 does not give me 18. I want a pair of numbers. Leave that up on the screen. And I'm going to travel over to the side and just write that again on the board. Because what we're hunting for is a nice selection of numbers. So I have 6x minus 5y equals 18. This is number 28, correct? Now my argument was x at 3, y at 0 worked. 3 0 works. 3 times 6 is 18, minus 0 is 18. Give me another pair that works.
Period or?
I want nice numbers. My definition of a nice number is integers. Anything that you can see that would work there. Anything at all that comes out of this process. Okay, what I'm hunting for is something that will give me an 18. And I'm letting y, as I look at it now, first, there's nothing I can multiply by 6 other than a 3 or like a 13 that's going to end in an 8. So I need a 13, a 23, something like that in order, or a negative 3. So if I go a negative 3, that's going to give me what? Negative 18, and I need to add something to that, and that's not going to do it to get to an 18.
What about x equals 8 and y equals 4?
Good choice. 6 times 8?
I'm sorry, 6. And
6 times 8 is
48.
48. Good. And what can I take from that?
Y equals 6.
Well, 30. So if I have minus 5 times 6, I have a minus 30, and that gives me the 18 I need. Do you see what the thought process going on here? It's a lot of mental arithmetic, but it's a good one to practice. 8, 6 worked. Now I have two ordered pairs. Now, if you don't like going through that, what could you do? You can say, well, let's let x equal 1. Okay. X is 1. 6 times 1 plus, I should say minus now, minus 5 times y is equal to 18. So minus 5y is equal to
18.
What?
18 over negative 5.
No. 12. Thank you.
Okay, because you
I had the 6 times 1 is 6, so I had to subtract 6 from both sides.
Right, okay.
I wasn't doing magic.
Okay.
Okay, so minus 5y is equal to 12, so y is what now?
Well, negative 12.
Negative 12 over 5, and that's negative 2 and 2/5, which is negative 2.2/5. 4/10. Sheesh. Negative 2.4. Now, is that as nice to graph? No. But it's a lot faster. You get 2 points and draw the graph. Now, I'm hoping that you get good at this, fast at it, and practice it. Now, last night's effort was throwing you to the wolves. A little bit. It's okay. You'll know how to do it better the next time you do it tonight. Okay, so hopefully that answers. I just had a comment both in class and on voicemail and email. Do something in 21 through 36, anything will help. So I hope I've done that in part of the lecture, and I hope I've answered the question, why are we doing this in the first place? So will you fold and pass, please? Okay, and we'll just leave that up there for a moment. We'll come back up here to the center. So that was the fold and pass bit. Where is the homework? It's up here in front. It'll come back there eventually, Laura. Now, while we're doing that, to come back to a problem in the book, 198. This gets back to my earlier presentation. This is on page 198. Here's a case where you're looking at the sporting goods sales based by year from 88 to 96. And what is it suggesting? That when you look at the data, you're going to have a line, and the data is given to you over here. Remember my comment, trying to get a line with as many points as in the line as you can? That was a bivariate data analysis, and that's being presented to you as part of what's done on 198. Coming off that, by the way, was direct variation. Here's another problem of a related type. This graph on page 199, number 47, shows you what? The value of a certain automobile based on what? The number of years after you bought it. Now you know the story. Drive it off the lot and you just lost a bunch. The question is how much? Well, it depends on the car. But ultimately, at some point, what happens? The value is less than you owe in 5 years. Notice this car is not paid off in the 5th year. And what is your usual dilemma? You need to replace the car and it's worth less than you owe, and you get into a real difficult situation. In fact, there's even a problem with insurance, because if you wreck the car and it's totaled, its value may be what? Less than what you owe, and then they're paying you money to pay off a car, and you have no money to replace the car now. So you can actually buy insurance that protects against that.
Insurance.
So there's something said for it. Now that is all part of what we just did in 3.2. So guess what part of your homework is going to be tonight? It's going to be going back and looking at problems like this, where you're looking at graphs and trying to answer questions. The problems are after the 36th problem that we talked about. So we have 43, 44, 47, and 48. So we can certainly get part of that now as part of your homework for tonight. So on pages 198, 199, 43, 44, 47, 48. So I'll just write these numbers over here on the left. 43, give me the numbers again. 43, 44, 47, and 48. And those relate to that question that was asked about applications problems that relate to using information that's linear. Okay? Now the question, can we find some more problems for you to graph?
I'd like that. I would.
I think it will help. And so what I need is a few more that you can do. And so as we look at 13, 14, 15, 16, and this is on page 196, these problems are doing what? See if I can get this down far enough we can read what I have here. You're to find what? The x, okay, we can cut to the document cam, the x-intercept, y-intercept, to use that as a form of graphing. So on this same set, as we come off there, we are going to do what? 13. So 13 through 16 all. This is still in set 3-2. Okay, so still doing, okay, we'll try to avoid this over here, Ernie. We'll just cover, the numbers, but not the wall. And then would it help on 7 through 12, where they set up partial solutions for you? Those are sort of developmental problems on 7 through 12, where what you're doing is they give you an equation, they give you half of the ordered pair, you get the other half. It's sort of, I feel sometimes like trying to close the door after the chickens have flown the coop, in the sense that it might have been better to have you do some of those early on, but maybe 7 through 12 would be a good part. So why don't we make it 7 through 16 all? So I'll just modify this up here. So 7 through 16 all, and 43, 44, 47, 48, and coming back now, front and center, you've heard me talk about it. Let's go to the document cam. The slope of a line. Okay, what do we mean by the slope of a line? Now, Ernie, behind me there is, let's leave this on the document cam for a moment, but there is that little triangle to my left where I have a line drawn and I talk about the slope, so let's go to that diagram. This diagram involves the slope of a line. So as I have a line and I have one point and go to the second point, there's an ordered pair here and an ordered pair here. Now the rise, as we call it, a little bit like when you build a staircase, the rise is the height of each stair. That's called the rise. It is y2 minus y1. Rise is y sub 2 minus y sub 1. The run, which is this part of the stair, as you go from point 1 to point 2, so we change x that much. So this is called the run, and it is x sub 2 minus x sub 1. The slope is just the ratio of those two. Rise over run. The slope is called m. So when I had this symbol here for m, that was slope. So the slope, let's see, we'll have to come over here, is going to be rise over run as I go from one point to another point on a line. Now I'm going to look at an example in the book. So I'll leave that there and I'll just walk off camera. Leave that there, Ernie, for a moment, please. The statement I have just written on the board is given to you on page 201 as we come to the book. M, the change in y over the change in x, and notice y sub 2 minus y sub 1 over x sub 2 minus x sub 1. I am referencing subscripts. So if we come off there for a moment, the argument is, and I'm not sure I have something in the form I'd like to see it. I'd like some positive slopes here, and I'm not finding it. So Ernie, what I'm going to do is we're going to go to the sideboard, and I'm going to finish off very quickly here with a problem in which I look at these points in the usual reference. So let's come back to the document cam. There's your formula. Now I'm going to look at a problem in which I have a line moving up to the right, something like this. Bad line there. Okay, now this is x, this is y. If this is my first point, I'm going to call that point 1 as I go from left to right. So this is going to be at x1 with a height here of y sub 1. So I indicate my pair as x sub 1, y sub 1. Out here, further to the right, is another point at x sub 2. Its height is going to be coming across here at y sub 2. So that ordered pair, x sub 2, y sub 2, notice the change, y sub 2 minus y sub 1. The change here, x sub 2 minus x sub 1. So if you get two pairs, the one on the right is going to be called point 2, and the one on the left is point 1. That's just very typical notation. So we'll leave that there, and what I'm going to have you do is find me some slopes for homework. So as we come back up here in front, I'm just going to ask you to find the slopes given some pairs. So the pairs, I want you to graph the pair of points and find the slope. We're on page 208. And that is going to be starting at problem 16 on page 208, and it goes through problem 25. So as we come off there, that's number 16 through 25 all. I need to write that on the board now. So this is page 208. So page 208, numbers, and that was 16 through 25 all. So you have splitting sections a little bit here, but that's what we're going to do for homework. Write the equation. You're going to pull the door shut so we aren't hearing that, please. Write the problem, draw the points on a graph, show the equation y sub 2 minus y sub 1 over x sub 2 minus x sub 1. You write the formula, show the substitution, and then the answer. So here is an illustration right above problem 16 in the document cam where I have the substitution. What's missing there is what? The y sub 2 minus y sub 1 over x sub 2 minus x sub 1. That you need to write in. So I want, again, to have you write in the formula. So let's come off there for a moment, Ernie. What would be written, I'll write here in a moment, as an equation. Okay, let's look at it again. That's not done with elegance, but that's the equation, y sub 2 minus y sub 1 over x sub 2 minus x sub 1, the substitution and the answer, and you're going to plot the points. Okay, Ernie, we had the Grateful Dead, and we had, how about Cumberland Blues? Do you know which one cut that is? We're going to go to Cumberland Blues with the Grateful Dead. Have a great day, and we'll see you tomorrow.